The overall goal of the following experiment is to prepare extremely pure and precisely defined organometallic molecules on surfaces so that structure-reactivity relationships and ion-surface interactions may be characterized using a combination of in situ SIMS and IR spectroscopy techniques. This is achieved by first preparing a solution of the organometallic compound in methanol and loading it into a syringe pump for injection into an electrospray ionization source. As a second step, collision-induced dissociation is performed in the high-pressure source region of the soft landing instrument, which removes one bipyridine ligand from each doubly charged ruthenium tris bipyridine ion, forming highly reactive undercoordinated doubly charged ruthenium bis bipyridine ions. Next, mass selection is achieved using a quadrupole mass filter followed by soft landing in order to prepare surface-bound organometallic ions without any contamination from unwanted species, solvent molecules, or counterions. SIMS and IRIS are used for in situ characterization of the surfaces. Results demonstrate organometallic ions immobilized on self-assembled monolayer surfaces by soft landing of mass-selected ions.
The main advantage of this method over existing techniques such as spin coating and drop casting is that mass selection enables atomically precise control over the size, charge state, and composition of materials delivered to surfaces.
This method can help answer key questions in the energy storage field, such as whether the size and ionic charge state of redox-active metal oxide clusters can control their structure and stability on surfaces.
Though ion soft landing provides insights into the sensitivity of catalytic and energy storage materials to size and composition, it has also been applied to other systems such as peptides, proteins, and viruses that have broad applications in biological sensing and diagnostics.
First, place a previously prepared self-assembled monolayer or SAM surface onto one of 3 metal sample mounts. Open the sample introduction door and secure the sample holder firmly to the manipulator inside of the instrument. Following this, close the door and open the valve to the 4-line mechanical vacuum pump. When the sample introduction chamber reaches a pressure of 10 to the -3rd torr, turn on the turbomolecular vacuum pump and ionization pressure gauge. When the sample introduction chamber reaches a pressure of 10 to the -6 torr, open the gate valve to the soft landing chamber. Use the magnetic manipulator or XYZ stage to position the SAM surface in line with the ion beam to begin soft landing. For each instrument, load 0.5 milliliters of previously prepared 0.01 millimolar tris 2,2'-bipyridyl dichlororuthenium-2 hexahydrate solutions into a 1 milliliter glass syringe. Mount the syringe into a syringe pump and apply +2 to +3 kilovolts to the capillary to generate positive ions. Then, adjust the syringe pump flow rate to between 20 to 40 microliters per hour to obtain an optimum ion current of the surface. Adjust the quadrupole mass filter to the mass of the doubly charged ruthenium bis bipyridine ion. Then adjust the voltage settings of the ion optics and radio frequency ion guides to maximize the ion current and stability of the doubly charged ruthenium tris bipyridine ion measured at the SAM surface. Following this, increase the potential gradient in the high-pressure collision quadrupole region of the soft landing instrument to enable gas phase ligand stripping from the organometallic ion through collision-induced dissociation. Upon completion of the deposition, turn off the syringe pump and the high voltage to the ESI emitter. Use the magnetic manipulator to move the prepared surface from the soft landing chamber to the analysis stage inside the TOF SIMS part of the instrument. Next, disengage the manipulator from the sample and retract it fully from the SIMS analysis chamber. Close the gate valve between the soft landing and SIMS part of the instrument. To conduct the TOF SIMS experiment, load the instrument control file in the software and ensure that the gallium ion source is producing a sufficiently stable current of primary ions. Acquire X and Y-axis line profiles across the surface to determine the center of the deposited spot of ions on the substrate. Position the surface so that the gallium primary ion beam is incident on the center of the deposited spot of ions. Then acquire a TOF SIMS mass spectrum for 5 minutes. Following this, turn off the primary gallium ion beam and the high voltages of the TOF SIMS instrument. Use the magnetic manipulator to move the sample back into the soft landing part of the instrument. Use a high vacuum leak valve to introduce a controlled flow of ultra-high purity oxygen gas from a cylinder into the instrument. Use the adjustable gate valve to throttle the pumping speed of the pump to achieve a steady state pressure of 10 to the -4 torr of oxygen inside the soft landing chamber. Repeat the previous steps to characterize the soft-landed ions following exposure of the surface sequentially to oxygen and ethylene for 30 minutes. Position a circular SAM surface at the rear trapping plate of the ICR cell located inside of the 6 Tesla magnet. Then use a cesium ion source to create a continuous beam of 8 kV cesium primary ions. During this, trap and analyze the secondary ions ejected from the surface using FT-ICR-MS. For infrared reflection absorption spectroscopy, direct the infrared light from the spectrometer onto the carboxylic acid terminated monolayer surface positioned inside the vacuum chamber. Utilize a gold-coated flat mirror to direct the light exiting the FTIR spectrometer onto a parabolic gold mirror. Next, reflect the light from the parabolic mirror through a mid-infrared zinc selenide wire grid polarizer and into the vacuum chamber through a viewport. Position the reflective SAM on the gold surface inside the vacuum chamber at the focal point of the first parabolic mirror using the motor-driven Z translator. Then, reflect the IR light exiting the vacuum chamber from the surface of the SAM through a second viewport. Use a second parabolic gold mirror to focus the reflected light from the surface onto an MCT detector. Finally, acquire spectra at set intervals during the deposition process. A peak corresponding to a ruthenium bispyridine thiol covalent adduct at a mass-to-charge ratio of 700 is observed here, which indicates very strong binding between the undercoordinated ion and the monolayer surface. The peaks corresponding to this species are featured prominently here. Presented here are the in situ TOF SIMS spectra obtained directly following exposure of the carboxylic acid terminated SAM surfaces containing soft-landed doubly charged ruthenium tris bipyridine ions and doubly charged ruthenium bis bipyridine ions to gaseous oxygen. The peaks are consistent with the addition of atomic and molecular oxygen to the organometallic surface adduct respectively. Moreover, this adduct appears to be oxidized with close to 50% conversion efficiency. The TOF SIMS spectrum following exposure to ethylene indicates a decrease in the relative abundance of the singly oxidized organometallic adduct at a mass-to-charge ratio of 716. A scheme describing what is achieved for this representative system through the combination of ion soft landing and analysis by in situ TOF SIMS is presented here. Representative results for doubly charged ruthenium tris bipyridine ions landed onto the carboxylic acid terminated SAM surface are presented here. During soft landing, the doubly charged ruthenium tris bipyridine ion exhibits a linear increase in abundance on the carboxylic acid terminated SAM surface. The measured abundance reaches a maximum at the end of soft landing and is followed by an extended plateau on the carboxylic acid terminated SAM surface. The singly charged ions, in comparison, are depleted more rapidly following the end of soft landing. The infrared spectrum obtained following soft landing of 5 × 10⁻¹² doubly charged ruthenium tris bipyridine ions onto the carboxylic acid terminated SAM surface is presented here. 9 vibrational features are noted with an asterisk in the IR spectrum as unique spectroscopic signatures of doubly charged ruthenium tris bipyridine.
Once mastered, the soft landing experiment can be set up in less than an hour.
Following deposition, the sample can be characterized using AFM, TEM, and STM to further examine the surface coverage and secondary structure of soft-landed ions.
After its development, this technique paved the way for researchers in the field of catalysis to explore structure-reactivity relationships in clusters and nanoparticles with unprecedented precision.